let's see Newton's second law of motion. So here Newton's second law of motion, in this law Newton stated that the time rate of change of momentum okay, of a body is directly proportional to applied force. Okay, in the theory of momentum, okay, in the last we take one example of rotated stone and we say that how the time rate of change of momentum is depends on what applied force. So here from it Newton's second law of motion, okay, Newton stated that in this law that time rate of change of momentum of a body is directly proportional to applied force, and that change takes place in the direction of applied force. Means change in momentum, okay, takes place in the direction of applied force. So here we can say, suppose a body of mass m moving with velocity v, okay, so here I can say, so its momentum is p equal to mv. Okay, now if under the action of applied force F, सपोज ये जो बॉडी है उसके ऊपर हम लोग क्या कर रहे हैं, फोर्स अप्लाई कर रहे हैं, ठीक है, ऑब्वियसली उसकी वेलोसिटी चेंज होगी, मतलब मोमेंटम चेंज होगा. सो हियर वी कैन से नाउ इफ अंडर एक्शन ऑफ अप्लाइड फोर्स F, its velocity is changes from v to delta v, then in time delta t, then we can say change in momentum is what, delta p is equal to what, we can say m delta v. Okay, so according to second law of motion, we can say, according to second law of motion, here I can say the time rate of change of momentum of body is directly proportional to applied force. So here I can say F is directly proportional to what, delta P by delta T. Now let's removing this proportionality. So here we have to put what, proportionality constant. So here I can say F is equal to K delta P by delta T. Okay, here for simplicity we will take value of K is equal to 1. So here I can say, for simplicity, value of K is equal to 1. So we will take value of K equal to 1. So here I can say, therefore F is equal to delta P by delta T. Okay, here we can say for time infinitesimal small time period. Okay, for infinitesimal time period means we can say delta t tends to 0. Okay, means whenever the time interval is very small. Okay, so we have f is equal to limit delta t tends to 0 delta p by delta t. So it will becomes what? Differentiation of momentum with respect to what? Time. So here we have f is equal to what? Dp by dt. Therefore I can say f is equal to what? Dp by dt. Okay, here we know that it is the differentiation of momentum, and momentum p which we have is equal to what? Mv over here. So d by dt of what? Mv. Okay, here you can see that we have to differentiate this term. So in this term mass is constant, so m remains as it is and dv by dt. So f is equal to what? M dv by dt. So here I can say f is equal to m. We know that differentiation of velocity with respect to time gives us what? Acceleration e. So we have the result of second law of motion, which is f is equal to ma over here. Now from it, if we take the unit of force, then you can say that mass is measured in a kg, while the unit of acceleration is what? Meter per second square. So here we can say unit of force is kg meter second minus 2 from here. Okay, now you can also find the dimensions of the force over here, which will becomes m1 l1 t minus 2. Okay, now from this second law of motion, let's take some important key points. Okay, some important notes, you can say. Note number 1. Okay, here you can see that if acceleration of the body is 0, then we can say force is also 0. So here I can say if, आप उल्टा भी लिख सकते हो कि if applied force is 0, then acceleration of particle is 0. So here I can say here if applied force f is equal to 0, then a is also 0, and we can say if acceleration is 0, then velocity is what? Constant. So here I can say v is what? Constant. Okay, here as the velocity is constant, okay, therefore I can say the Newton's second law of motion is once again indicates what? First law of motion. It represents what? First law of motion. How? Because in first law of Newton's, okay, we already न्यूटन का जो लॉ ऑफ मोशन था फर्स्ट हमने देखा था कि unless any external force acting on a body, okay, it will maintain its state either at rest or uniform motion. Means we can say body continuously to be its state of rest or state of uniform motion unless it is compelled by any external force, okay, to change its state. जब तक आप कोई बॉडी के ऊपर फोर्स अप्लाई नहीं करते, ठीक है, वो अपना स्टेट ऑफ रेस्ट या स्टेट ऑफ यूनिफॉर्म मोशन मेंटेन रखेगा. तो आप जब तक फोर्स अप्लाई नहीं करते उसका स्टेट ऑफ यूनिफॉर्म मोशन मेंटेन रहता है, मतलब वेलोसिटी कांस्टेंट रहती है, ठीक है, विच इज द व्हाट? फर्स्ट लॉ ऑफ मोशन. एंड हियर दिस विल आल्सो रिप्रेजेंट द फर्स्ट लॉ ऑफ मोशन. So here we can say the second law of motion represents first law of मोशन, ये फर्स्ट लॉ ऑफ मोशन ही रिप्रेजेंट करता है, ठीक है। नाउ वी नो दैट फोर्स इज व्हाट, वेक्टर क्वांटिटी, फोर्स वेक्टर क्वांटिटी है, एक्सेलरेशन भी वेक्टर क्वांटिटी है। सो दिस लॉ व्हिच इंडिकेट्स द F is equal to m as the second law of motion, it is a vector law. So here we can say the second note is what, the second law of motion is a vector law. Okay, so here if the force acting on the body, okay, has its component in x, y and z axis, okay, then we can say there must be change, okay, in its momentum, which is delta p, in x direction, y direction and z direction, and it has the acceleration in all the three dimensions, means we can say it has a component of acceleration in all the three dimensions. So here I can say x component of force, okay, let it be fx. So fx is equal to, I can say, dpx by dt, and that is equal to, I can say, max. Okay, now for y component, I can say y component of force is equal to dpy by dt, and that is equal to may. Okay, and the third one, z component, that dpz by dt is equal to maz. Okay, means over here I can say the x component of force, okay, is equal to what, mass into acceleration, which is only in x direction. Okay, so here if there is some angle between velocity vector of a particle, suppose particle, or you can say body, which is at p, having a velocity vector is in this direction, okay, and force is acting in this direction and having an angle theta between them. So here you can say velocity vector and force both are having an angle theta between them, then here you can see that this body, okay, as a two component of velocity, this component of velocity is v cos theta, and this one becomes what, v sin theta. So in this case the force will change the velocity which is in its direction only. So here we can say the force will change the component of velocity which is in the direction of force, okay, the other component of velocity does not change, it will remains constant. तो ये वाली velocity change हो जाएगी, ठीक है, which is in the direction of force, but the component of velocity which is perpendicular to force over here, this one will remain constant, it will not change. Okay, so here we can say the force in x component x direction में force है, ठीक है, तो आपका acceleration max होगा, y डायरेक्शन में जो वेलोसिटी का कंपोनेंट है वो क्या रहेगा, as it is रहेगा, ठीक है। So here I can say if there is an angle between, you can write the statement like that, if there is an angle between force and velocity, okay, then due to that force a component of velocity which is in the direction of force will only change, the other component of velocity remains as before. Okay, now let's see the third note over here. If this equation is applicable, okay, only for any particle, okay, a single particle, then we can say whenever the force F is equal to this equation, second law of motion, which indicates second law of motion is applicable for a single particle, then we can say F is the force acting on that particle and A is what, acceleration of that particle. But whenever the equation, this equation is applicable for a rigid body, a body which opposes any change in its shape, that is called rigid body, okay, which follows the inertia, we can say. So whenever this second law of motion, or you can say this equation F is equal to ma is applicable to rigid body, which is also called, you can say, a particle, or you can say system of extended particles. Okay, large number of particles means you can say एक ऐसी बॉडी, ठीक है, रिजिड बॉडी जो अपने शेप में चेंज होने से अपोज करती है, इसको आप कंसीडर कर सकते हो. सपोज ये रिजिड बॉडी है, ठीक है, सो इट कंटेन्स लार्ज नंबर ऑफ पार्टिकल्स. ओके, सो इट इज ऑल्सो कॉल्ड एज सिस्टम ऑफ पार्टिकल्स. ओके, सो व्हेनेवर इट इज एप्लीकेबल टू सिस्टम ऑफ पार्टिकल और rigid body, in that case F is the force applied on a system of particles. F is the net force applied on that system of particle, and A is what? A is the acceleration of whole system, okay, of the particles. So this one is the note number 3, and the fourth note, which is very important, okay, that force, okay, or you can say acceleration first. Let's start from acceleration. That acceleration of a particle at any instant, okay, at any moment, at any point, okay, depends on force acting on that body on that instant, okay, on that point only. बॉडी जो है उसका एक्सेलरेशन कोई भी पॉइंट पे, कोई भी इंस्टेंट पे सिर्फ और सिर्फ किसके ऊपर डिपेंड करता है? वो बॉडी पे उस इंस्टेंट पे, उस पॉइंट पे जो फोर्स लग रहा है उसके ऊपर डिपेंड करता है, ठीक है. सो हियर यू कैन से acceleration of a particle at any instant, at any position, at any point depends on what force acting on that instant, on that point only. Means the stone, if we are drop one stone from an accelerating train, once again the train is accelerating, okay, so inside this train, okay, if I am standing on that train, okay, and I have one stone in my hand, if I drop it, okay, then what happen? Let's understand the situation very clearly, that before dropping the stone, okay, train is accelerating, so we can say with respect to ground the stone is also accelerating, means the stone has a acceleration before it is dropped. But the moment after which the stone is dropped, okay, stone has no horizontal acceleration. स्टोन के पास कोई horizontal acceleration नहीं होगा क्योंकि उसको ड्रॉप कर दिया है. सो हियर वी कैन से stone carries no memory, okay, of its horizontal acceleration once it is dropped from the train. Okay, so here we can say the acceleration of the particle at any instant, okay, at any point depends on what force acting on that instant at that point only, which is the note number 4. Okay.